For a function of two variables, z equals f of xy, delta x and delta y are increments of x and y. The increment of z is delta z equals f of x plus delta x, y plus delta y, minus the original function f of xy. Definition: if z is a function of two variables x and y, and delta x and delta y are increments of x and y, then differentials of the independent variables x and y are dx equals delta x and dy equals delta y. And the total differential of the dependent variable z, which was your function of two variables, is given by dz equals the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Example, find the total differential for each. Well, we're going to start with function z, which is a function of two variables, defined as 2x times sine y minus 3x squared y squared. The total differential dz is going to be the partial derivative of our function with respect to x times dx plus the partial derivative of our function with respect to y times dy. The derivative of the first term with respect to x, we have an x term here, so that's a derivative of 2. So our partial derivative is 2 sine y. The second term with respect to x will be negative 6x y squared. So we have our partial derivative with respect to x times dx, plus then we go back through and we take the partial derivative of this function with respect to y. So that's going to be cosine y with our 2x in front, 2x cosine y, minus 6y with the x squared left alone, so negative 6x squared y times dy. If we move up to a function of three variables, and I'm just going to call it w, but define it as x squared plus y squared plus z squared, our total differential for this particular function of three variables, we're going to take the partial derivative of w with respect to x times dx plus partial derivative of function w with respect to y dy, and then finally we're going to do the partial derivative of our function with respect to z dz. Well, these derivatives are easy, so we've got 2x dx, 2y dy, and finally 2z dz. A function given by z equals f of xy, in this case two variables, is differentiable at a point x sub 0, y sub 0 if delta z, which is the change in your function value, can be written in the form partial derivative of f with respect to x of the point given times delta x plus partial derivative of your function with respect to y at that same point given times delta y plus epsilon 1 delta x plus epsilon 2 delta y, where both epsilons will approach 0 as the change in x and y gets smaller and smaller, or that point approaches 0. The function is differentiable in a region R if it is differentiable at each point in R. Example, show that f of xy equals x squared plus 3y is differentiable at every point in the plane. Okay, so we're going to let z be our function of two variables, and it's defined up here. The increment of z at an arbitrary point, which was dz, that's the increment of z, in the plane is given by, and this goes back to our last slide, f of x plus delta x, y plus delta y, minus the original function. So up here, I'm going to substitute x plus delta x for this x, y plus delta y for this y, and that's going to give us x plus delta x quantity squared plus 3 times y plus delta y minus the original function x squared plus 3y. Write this twice and FOIL it, and you'll get x squared plus 2x delta x plus delta x squared. This value comes from the O and the I of FOIL. Plus 3y plus 3 delta y minus x squared minus 3y. We get quite a few cancellations. X squared minus x squared cancels out. 3y minus 3y cancels out, leaving us with 2x delta x squared plus 3 delta y. Rearranging the terms, 2x delta x, 3 delta y, splitting this into delta x times delta x, and then since there's no delta y term, we can add, well, there is a delta y term, 3 of them here, but there's no harm in adding no more of them. See that little trick there? Letting epsilon 1 be delta x, epsilon 2 be 0. These will both approach 0 as delta x and delta y get smaller and smaller. That's because they're multiplied. Back up here, these first two terms, 2x, that's the partial derivative of our original function with respect to x, and 3 is the derivative of our function with respect to y. So we have partial derivative of partial derivative of f with respect to x times delta x, which is also dx. This is back up here in our definition, plus the derivative of f with respect to y dy. Therefore, the function is differentiable at every point in the plane. If we're asked to approximate by differentials, we can use this value for dz is equal to partial derivative of z with respect to x times delta x plus partial derivative of z, which will be our original function of 2 or 3 variables with respect to y, delta y. If there is a third variable, you would take the partial derivative of z with respect to the third variable, delta, whatever your third variable is. This represents the change in height of a plane that's tangent to the surface at the point x, y, f of x and y. Example, use the differential dz to approximate the change in this function as xy moves from 1, 1 to 1.01, 0.97. Note that the change in x is very small. In fact, 1.01 minus 1, there's only 1/100th of a value change in x, very small. The delta y, the change in y's, the value goes down 3/100ths. So anyway, if you want to calculate them by hand, that's fine. 1.01 minus 1, that's the change in x. 0.97 minus 1, that's the change in y. Now, back to our total differential. We're going to take the partial derivative of this function with respect to x times dx, and then we're going to plus take the derivative of this function with respect to y times dy, or delta y. We're going to follow this formula at the top of the page. Okay, so our derivative is not super easy, but it's not just overly difficult either. Rewrite this function as 4 minus x squared minus y squared, all in parentheses to the half. You can change that square root radical to 1/2. Now, using chain rule, because we've got to take a derivative with respect to the x term, we're going to take the derivative of the overall, which will be 1/2 4 minus x squared minus y squared to the negative half after you subtract 1 from your power, times the derivative of the x term underneath. So that's going to be 1/2 square root of 4 minus x squared minus y squared in the bottom, because when you use power rule, that resulting power becomes negative half. If you move it to the denominator, it becomes positive half, which can be rewritten as square root. This delta x is the change in your x value that increased by 1/100th. Plus, retake the derivative of this thing, so it's, again, treat this as all to the 1/2 power. 1/2 of 4 minus x squared minus y squared to the negative half. So here's our 1/2. When you move the negative half to the denominator, it becomes positive 1/2 as your power, translating back to a square root. And then the derivative of your y term is negative 2y. So these partial derivatives for this function, you got to be very careful. And then your delta terms are just the change in value. So in our y values, we decreased by 0.03. Now, when you calculate this differential at the point 1,1, you're going to substitute a 1 in for all your x's and y's. Carefully make this calculation. You can even cancel these 2's down. But anyway, long story short, partial derivative when x and y are 1, the other partial derivative when x and y are 1, multiply each partial by the change in x and y respectively, and this is our change in function value using the total differential formula. Now the exact delta x, or change in function values, if you just force evaluate f of the second point given minus f of the original point given, that's just brute force substitution. You will get these two values respectively, and they have a difference of 0.0137. You will find that a total differential approximation and an exact delta z will be pretty close and sometimes the same. Let's do one more example, and this one will integrate some trig into it. We're going to let f of xy be equal to x times cosine y. Again, I'm going to define z as our function of two variables. Let's find f of 8.3, f of 8.13.05, and then we'll calculate the change in the function value. F of 8.3 is 8 cosine 3. Make sure you're in radian mode. You will get an approximate value of negative 7.9199. The function with a direct substitution of 8.1 and 3.05, still in radian mode, will give you this approximation. It's a good idea to always round to 4 or more decimals. 4 or 5 are usually pretty typical. Now, the change in z, or the overall change in your function value, is those two function values subtracted. Negative 0.1461. If we use a total differential to approximate that, this is the exact change between these 2 point function values. The total differential for dz, or delta z, however you want to write it. dz is usually pretty typical for the total differential. Partial derivative with respect to x times delta x plus derivative of our function with respect to y, partial derivative with respect to y, times delta y. Well, let's go back up here. Here's our original function. if we take the derivative with respect to x, that becomes 1 cosine y dx. Delta x and dx, because these are very small incremental changes, can be used interchangeably. The derivative of the y term is going to be negative sine y, but don't forget the x attached because that's considered a constant. So it's going to be negative x sine y. That's that partial derivative, dy. All right, what are our change in x? To go from 8 to 8.1, that's an increase of 0.1. That's delta x. The change in y, there's an increase of 0.05. So that's our delta y. Partial derivative with 8, 3, that's our original point. 8 goes in for x, 3 goes in for y. Bring this right down, it's cosine of 3, dx is 0.1, minus 8 sine 3, dy is 0.05. Carefully type this into your calculator. Again, remaining in radian mode, you will get negative 0.1554. Very close to the exact function change. Let me know if you have any difficulties with this section, any questions. This will be posted in your Google Drive folder. I do plan to write up a few more homework solutions. You'll also find those in your Google Drive folder for the class under homework notes. And just reach out if you have any questions or concerns.